All right, so what we're looking at here is rates of change in exponential and logarithmic functions. We're focusing on the exponential functions. Rates of change we've done before. So I'm going to go through example 2 and 4 because what we're also going to do, and I think this is one of the most important things in real life math, is develop exponential equations. So every exponential equation is in the form y equals a times b to the power of x. Now, the key is that A, that's your starting amount. All right. And B, that is your multiplying factor. All right. So we get to example number 2. Like I said, I'm going to do 2 and 4. Money. Abby invests $1,400 in a savings account that pays her, a little bad English here, 7.5% compounded annually is what it should say. How much is in the account after 3 years? All right, so what we're going to do is come up with an equation first. Now, the first thing is she starts off with $1,400. That is your starting amount. All right, for this question. Now, we got to find the multiplying factor. Now, this money is increasing at 7.5%. Now, percent is useless in math to use for calculation. So what you have to do is convert it to a decimal, which means I got to divide this by 100. So I get 0.075. But here's the thing, is that not only when they have their money are they getting the 7.5%, but they're also getting all their money, which is 100%, which divided by 100, you get 1. And so the total multiplying rate is going to be 1.075. The 1 stands for that you're getting all of it, 100% of your money. This comes back to you. Otherwise, I wouldn't be investing. Plus, you get 7.5% more. And so the equation for this situation is y equals, the starting amount is 1,400. The multiplying factor is 1.075. And again, we have an x. So there we just developed an exponential equation. Now this is saying, A, how much is in the account after 3 years? And because this multiplying factor was 7.5% per year, that means my x is in terms of years. And so in this case, in A, we want to know how much is in the account after 3 years. All right, so I substitute that value in. So I have 1,400. I have 1.075 to the power of 3. All right, Bedman's got to do exponents first. So I take that 1.075, take it to the power of 3. I believe I get 1.24. I multiply it by that 1,400. And now in the account, I get $1,739.22. All right, so again, we come up with the equation by analyzing the starting amount, then doing the multiplying factor. Then we're adding 7.5% to our 100%, but again, percent is useless to you as calculations. You got to convert it to a decimal. And there we go, there's our multiplying factor. Now we get to B. Now this is something we have done, where it is asking for the estimate, the instantaneous rate of change. I'm going to get rid of this here. All right, so we want to estimate the rate of change after 3 years. So our x value is 3. All right, and again, when we're finding our instantaneous rate of change, I get to estimate, which means I don't have to do limits, which I know a lot of you are fans of. All right, so I need an h value. So our function, what am I going to call our function? The amount, I guess. The amount function of 3 plus an h. So I'm going to make my h value, again, 1/100th or 0.01. And so I'm going to call this my a function right here, the amount. All right, minus, so again, we're using our slope formula, a of 3, divided by, of course, our h value, which was 0.01. Now, you have to go ahead and plug A of 3 into the equation, which we already did. That's 1739.22. All right, so my instantaneous rate of change, we've already figured out that one. That's what in part A was asking us to do. I have a 0.01 here. Now I have to take 3.01 and plug it into my equation for my x value. And when I do that, I've already done it. I got 1740.47. All right, so I plug that in there. And again, just doing the math, subtract the numerators. So my instantaneous rate of change, I get, let's see here. Well, I subtract these two and I divide, I'm getting 125. And so what that is telling me, because it is an instantaneous rate of change, is that the money in the account, money, I guess I'm just going to short form here, I don't have much room. Money, it's positive, so is increasing. That's a key word when you're talking about rates of change, increasing or decreasing. All right, so because it's positive, the money is increasing at a rate of, and this 125 represents dollars and our units of time per year. So that's not telling us how much money is in the account. It's telling us how fast the account is growing at 3 years. So after 3 years, you're gaining $125 a year. That's at that point. That's how fast the account is growing. All right, so there is, again, we've done this instantaneous rate of change, but again, developing our equation. That's something new. All right, now go to example number 4, all about ants. Hopefully none of you have ever had an ant problem. All right, so just nice and dry. All right, so example number 4. The population of an ant colony is decreasing at a rate of 16% a month. Good. Looks like the traps got sent out. The current population of the ant colony is 850. All right, so it says write an equation that models this situation. So again, an exponential equation. We have y equals a times b to the power of x. Our starting amount. We're starting off with 850 ants, unfortunately. Now, your multiplying factor. You have all the ants to start. 100%. Again, as a decimal, that's 1.00 because we times it by, divided by 100. Now, it is decreasing at a rate of 16% a month. So it's decreasing. So I'm going to minus 16% here. And again, 16% as a decimal, divided by 100, 0.16. And so if I take 1 and subtract 0.16, I should get 0.84. And so therefore my equation that models this situation is y equals, there's my starting amount, 850. My multiplying rate is 0.84 to the power of x, where x is, the units are months on this one. All right, so there's my equation. The key for developing an exponential equation is if the amount is increasing, your multiplying factor is going to be over 1. If it is decreasing, your multiplying factor is going to be under 1. All right, so I did one of each. Now we get to B. Here's a little bit of a different situation here. Is estimate, so again, we're going to do the same slope formula. Estimate the rate of change of the ant colony when there's 500 ants. Okay, so normally what happens, like in the first example, we have the x value to do our instant rate of change formula. But I don't know when there's 500 ants, so I'm going to have to figure it out. So I'm going to take my equation And I'm going to find out this X value, the time in which we have 500 ants. And so that means my Y value here is that. So Y is I have 500 ants, start with 850, and here's my multiplying factor, 0.84 to the power of X. Now this is something, again, we've done, solving an exponential equation. So we're going to have to use logs. But I'm going to have to get rid of this 850 first. So I'm going to divide both sides by 850. I'm going to do to one side, I do to the other, so they're gone. That is going to be 0.500 divided by 850. I get 0.588 equals 0.84 to the power of X. And again, got to use my log rule to get my exponent down to be a normal number. So I'm going to take the log of both sides. All right. That again brings that value down. All right, so log of 0.588, very small number. The log function makes it even smaller. I'm getting negative 0.231. The log of 0.84, again, a very small number. I'm getting negative 0.076. And the last thing, I got to divide by my numerical coefficient here, all right, to get X by itself. And I'm going to have, let's see here, divide by negative 0.76 on both sides. And my X value is, I'm getting 3.04 months. So that is when there is 500 ants. Okay, so it takes a few months. It's decreasing by 16%, but when there's 500 ants, it's 3.04 months. And that's when we want to know the instantaneous rate of change. So now I'm looking at, there's my X value. Again, I'm going to pick my H as 1/100th. All right, so I'm going to find, I guess I'll call this the amount of ants again, the amount function. So I have my instantaneous rate of change is equal to, I'm looking at the amount. So I have my X value plus my H. So 3.05 minus the amount at 3 months, or sorry, 3.04 months, because that's our X value, all over our H value, which is 0.01. All right, now I know this amount at 3.04 months. It was 500 ants. So I find my instantaneous rate of change. I know that the amount at 3.04 months is 500, because that's what we used to calculate it, divided by 0.01. What I do need to do, though, is separately figure out when I plug in 3.05 into this equation, and I've already done that. And that amount for 0.305, I did a little bit of calculating. I got 499.43. What did I say? 499.43. Okay. So I plug that in. All right, and then again, I'm going to subtract the numerators, divide by the denominator. Let's see what I get here. So I take 499.43 minus 500. Okay, negative. I get a negative answer. Divided by 0.01, negative 57. And so, finally, therefore, because I'm going to ask you for a concluding statement, right? You've got to be able to interpret what the heck is going on here. So therefore, the ant colony, and keywords here when we're talking about rate of change, is negative sign decreasing at a rate of 57 represents 57 ants. And again, our X value was in months, so it is decreasing at a rate of 57 ants per month. All right, so that example right there there's two of them on this note, but it's taking into two things that we've been doing: solving an exponential equation, doing an instantaneous rate of change, and also today coming up with your own exponential equation. All right, so that's a lot of things together, but again, everything we've done, but all of a sudden it's all together. So that's what makes this tough, I think.